Question number 3. Yeah. Simple, yeah, finding minimum selection problem. Yeah. So this whole quiz number 2, pretty hard, but this question is easy. Yeah. So I hope for most of you, usually I give you a few easy questions each quiz. Yeah. So, but I hope you should not miss those easy questions. Yeah. Also in homework, I like to give you some, easy questions. Yeah. I feel not right to give you all hard questions. So that's not right. So we should keep some balanced way. Yeah. Easy, middle level, and hard. Try to, using some balanced way. Yeah, for the question difficulties. All right, yeah. Next question. When we calculate the limit of the ratio to growth function, we can always apply no, because we need to check if that ratio is an indeterminate form, false. Because we need to make sure the indeterminate form for this class, we only need to check infinity over infinity indeterminate form. Yeah. In calculus, there are many, 5 or 6, the total number indeterminate form, at least 5 or 6. But we only need 1 here. For other cases, so you do not need it. But there is a condition you need to check. Okay, so that's covered in the notes. Number 5, an exponential function with a base greater than 1 always grows faster than that of, we can say true. Always grows faster. When we say grows faster, grows, right? So grows, it's we describe some behavior in the future. So we may not worry about relatively small n numbers, because we're looking at the growing trend. So the future trend, that kind of thing. That's correct. That's correct. When we consider n larger and larger, so we know the exponential function a to the n grows faster than the polynomial. Here it's a polynomial. Polynomial, the dominant term of polynomial is a power function, right? The dominant term or the leading term. All right, number 5. Number 6. This one, linear search, we have a formula. So if you go back to the notes, but I said here exact number, not approximate number. Because some of you may like to ignore some minor terms, use a simplified version of the formula. But here we should use the full version, not simplified version, the original version, the formula. So that's 1/2 times m plus 1 times p times n times 1 minus p. Okay, p 0.8, so 1/2 times 101 times 0.8 plus 100 times 0.2. Okay, yeah. So make sure your calculation is correct. So 1/2, 0.8, 0.4. So 0.4, 40.4. All right, yeah. Plus 20. So the answer 60.4. Okay, yeah, 60.4. Yeah. All right. But here the main thing is, I'm afraid some of you may drop that 0.4 because you feel number of comparisons should be integer, although number of comparisons should be integer, but when you see the average number of comparisons, when we talk about average of certain integers, we do not require that average to be an integer, right? Usually it's not an integer. Okay, so don't drop the the digits after the decimal point. Yeah, if I say something, so you can keep the precision to certain digit. Yeah, so you can do it. Yeah, if I do not say anything. Yeah, and here I emphasize exact number, so you should not drop that 0.4. Yeah. All right. Yeah. So the reason I make this question, so I try to convey this fact: the average is not necessarily an integer number, not necessarily an integer. So that point. Okay. Yeah. All right. Next, number 7, we went to sort 3-element array. Yeah, this array with small size, n equals 3. Okay, yeah, with distinct values. How many comparisons do you need to sort this array for the worst case? Answer is 3. Yeah, answer is 3. Yeah, but here, this problem size n equals 3, it's a small number, very small number. Okay, yeah. Yeah, why I emphasize this small number? Because usually many students, they like to apply some formula. Okay, yeah. So here because in the problem statement, I didn't mention any particular algorithm, right? I didn't say any algorithm. Selection sort, bubble sort. Yeah, all right, yeah. So I will, yeah. So here, let me see. We should not apply any, all right. Do not apply any formula. No. Let me explain. Yeah, I need to use a lot of, explanation, to, try to get your understanding right. Yeah. All right. So why? Yeah. Here, let me answer this question. Why? Okay. Yeah. All right. Think about this. When you apply certain formula, there is some algorithm behind it. Okay, yeah, talking about some algorithm. Okay, selection sort, bubble sort, and some other sorts. Okay? Yeah, but how do you know that algorithm would give you the best solution, right? Yeah, you do not know. That algorithm just gives you one of the solutions. One of the solutions. Okay? Yeah, but for this question, our goal, we want to find the minimum number of comparisons. Although how many, I didn't say minimum, but your answer should be the minimum, the best you can do. Okay? If it's not a minimum, you cannot get full credit. Okay? Only when your answer gives the minimum number comparison, you can get full credit. Otherwise, you can only get partial credit. Okay? Yeah. All right. But if you apply any formula, you apply certain algorithm, but you do not know that algorithm would give you the best solution. It may not be the best solution. Yeah. So here, what we should do, we forget about any algorithm here. We just work on 3-element array directly. Okay, and because this is a small number, the good thing about n equals 3, it's very easy to, work it out explicitly. When n is large, we cannot sort it explicitly, too complicated. But n equals 3, so simple. Then, we can do it. All right, so compare x1 and x2. Okay, yeah, all right. So we can assume x1 less than x2. Yeah, why we can that? Because usually in math we say without loss of generality, right? Yeah. So here we have this similar situation without loss of generality. Okay. Or sometimes people write, W, L, O, G, yeah, because people always use this way. Yeah. Try to make it as simple as possible. All right. So the next step, yeah. So this is the first comparison. The comparison number 1. Then you consider, comparison number 2. Yeah, you have different ways, but yeah. So let's say this. Yeah. The next step, compare x2 and x3. This time you cannot do that without loss of generality, yeah, because you will lose generality, right? Yeah, so you need to consider 2 cases. Yeah. Case 1, x2 less than x3. Case 2, x2 greater than x3. Okay, yeah, because we assume distinct values. So do not consider the equal case. Yeah. And in this case, you have solved it because x1 less than x2 less than x3, 2 comparisons, you get it sorted. But that's the best case. That's the best case, not the worst case. Okay. So this case, you do not get it sorted. So you need another comparison. Compare x1 and x3. Yeah, you have 2 cases. Yeah, but you need a third comparison to get it sorted. Okay, so this comparison number 2, comparison number 3, and you get it sorted. Yeah, 2 different cases, but you need a 3 comparison to get it sorted. This is the worst case. Okay, yeah. So this is your solution. You work it out. You work it out explicitly in this way. Okay, yeah. There is no name for this algorithm, right? Yeah, no name. Okay, yeah. Because in this way, you know, that's the best solution. Yeah, that's the best solution. Okay, yeah. Nobody can use fewer than 3 comparisons to solve this problem. Yeah. Then people may argue, here, although this is the best we can do, but people may ask you this question: how do you know this is the best? Right? Think about the question we discussed in part 1. Yeah, the part 1 before our break. You know, in order to say this is the best solution, you need to rigorously prove it, right? Here, we didn't rigorously prove it. Yeah, here we, just based on our, intuition, yeah, so we cannot do better. No, it seems like nobody can do better, but no proof for it, right? Think about that. No rigorous, no proof for it. How do you know this is the best? Okay, best or not? Yeah, yeah. So, it will be. Don't say that quick. Yeah, not false. Still correct. Still correct. Okay. Yeah. So, but here at this point, we do not have enough knowledge to prove it. Okay. It could be proved, but at this point, we do not have that knowledge to prove it. Yeah. Later, if we have chance, yeah. So I hope we can find some time. I will prove it. Yeah. But here I can give you the formula. Okay. Formula. Yeah. Formula for the lower bound. So here, yeah, when we talk about lower bound, I can only say a lower bound. Yeah, because it may not be unique, right? Yeah, the lower bound, could be this one, that, different lower bound. But here I just give you one lower bound. Yeah. For the lower bound. Yeah, I do not write because I do not have that much space here. The lower bound for the number of comparisons to sort n element array. Okay, yeah. We want to sort. This one is n element. Okay, n element array. Lower bound. Okay, yeah. What's that lower bound? All right. So that lower bound, ceiling function of log base 2 of n factorial. This is the lower bound formula. Okay? The lower bound, so that means nobody can do better, fewer number comparison than this number. Okay? No matter what algorithm you use, this is a lower bound. Yeah. you can reach it. Your number could be the same as this one, but could not be smaller than this one. Yeah, so this is, an absolute lower bound. All right. Yeah, but here, if you plug in 3, so let's look at the seeding function of log base 2 of 3 factorial. How about that? Log the base 2 of 6, right? 3 factorial. Seeding function, that's 3, right? Yeah. That's 3. 2 point something. Yeah, less than 3. 3, 2 to the third, that's 8, greater than 6. So log base 2 of 6, seeding function, it's 3. That means the lower bound is 3. Based on this lower bound formula, we already reached the smallest possible number to solve a 3-element array. That's the best. Nobody can do better than this lower bound, right? We reached that lower bound. Nobody can do better than the lower bound. Yeah. But we delayed this question. How do you know this is lower bound? Yeah, because it requires another important piece of knowledge called a decision tree. Yeah. After I introduce the decision tree concept, or decision tree method, we can treat as a method, not just concept. It's a method. After I introduce the decision tree method, then we can derive this lower bound formula. Okay, yeah. So this lower bound formula covers all the possible sorting algorithms. Yeah. Even here, we cannot exhaust all the sorting algorithm, right? Nobody can exhaust all the sorting algorithm, but this formula covers all the comparison-based algorithm. Comparison. If your sorting is based on comparisons, then this formula covers it. Okay, yeah. But there are some non-comparison-based algorithm. Yeah, there is certain non-comparison-based sorting. Yeah, so, yeah. But here, this lower bound for comparison-based sorting algorithm. All right. Yeah. So here, because after I give you this formula, you can apply it. Okay. Yeah. But at this point, it is a little early. Yeah. A little early at this point. Okay. Yeah. Yeah. But because I give you the formula, so when you have a chance, you can apply this formula. Okay. But later, I will try to prove it. I will try to derive this formula. Okay. Yeah. So then you will see it is correct. This formula is completely correct. Okay. Yeah. All right. Yeah. So next question. Yeah, I need to erase, yeah. Although I can put more space, but oh, sorry. Yeah. Yeah, this question I mentioned a little bit when I talk about homework assignment. So now, probably when you work on the quiz, you do not know Pascal's triangle, right? Yeah, here. Yeah, but yeah, let me see. Yeah, you do not know the Pascal's triangle. Yeah, and now you know 1 plus x to the 4th. Okay, and you know you need to do square twice. Yeah, you need to do square twice. So 2 multiplications. Okay, the minimum number multiplications 2. So this one, I guess, probably most of you missed this one. Yeah. So most of you missed this one. Yeah. 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 But the good thing is, I do not give you too many questions like this one. Yeah. In this quiz. Yeah. I just want to challenge you a little bit. Okay. Challenge you a little bit. Yeah. All right. Yeah. Dakota's question. So if we have 4 elements, good. N equals 4, it will be 20. Yeah. So here you didn't apply the formula completely. Yeah. So you missed something. All right. So here, our original formula is log base 2 of n factorial. You didn't take log base 2 operation. All right. You take the factorial, but not log base 2. You missed that log base 2. All right. So log base 2 of 24. What's that number? Ceiling function. Power of 2. Power of 2. 24 is between 16, that is 2 to the 4th, and 32, that is 2 to the 5th. Okay, yeah, 2 to the 5th. So ceiling function, that's 5. Okay, the best you can do to sort 4-element array with comparisons, 5 comparisons for the worst case. 5 comparisons for the worst case. If you can do it with 5 comparisons for the worst case, that means your solution is optimal. Okay? Yeah. Based on the formula, lower bound formula, your solution is optimal. Okay? Nobody can do better than 5 comparisons for the worst case. Okay? So here you have another optimal situation, right? Yeah. Because the formula can be rigorously proved it's correct. Okay? It is correct. Okay? It covers all the comparison-based sorting algorithms. All the comparison-based. Okay? Even most of them, we do not know their names. Probably no names. Yeah. It's not important. Yeah. But our decision tree method can still cover those unknown sorting algorithms. How about that? Unknown sorting algorithms. Here, because there are most of those algorithms unknown. Unknown sorting algorithm. Okay, yeah. Unknown sorting algorithms. That's lower bound formula. Covers all those, known or unknown. Doesn't matter. It covers all comparison-based sorting algorithms. Can you believe it? Is that possible? Think about that. Is that possible? Yeah. Because unknown algorithm, think about this. Since it's unknown, nobody knows the details, right? When we talk about certain unknown algorithms, nobody knows the detail of those unknown algorithms. How can you study those unknown algorithms without knowing the details? Can you still study those unknown algorithms without knowing their details? The question is yes. Even unknown, even a lot of details missing, but we can still study those algorithms. Interesting? Interesting? Yeah, why? Because the reason, so here, I don't, yeah, I need a little more space. Yeah. All right. So let me borrow the space of this slide, then I erase it. Now, so the question, why we can study those unknown sorting algorithms without knowing their details. Okay, without knowing their details. Yeah, let me explain this. Yeah, we need to do that. Okay, we need to do that. Yeah, here I'm talking about the lower bound formula. Yeah, let me put it here. Because when we derive this formula using that decision tree method, our method covers all those comparison-based algorithms, known or unknown, doesn't matter. It covers all of them. Yeah. Why it's possible? Yeah. Because we can discover some common properties for all those algorithms. Known or unknown. Even unknown, but we can discover some common properties they have to follow. That's the most important thing. Yeah, we may not know the details, but we, we can do this. Common properties they have to follow. All the comparison-based sorting algorithm, they have to follow certain properties. And we can discover, we can find those properties. Then we can study. We just study those common properties. When they do comparisons, they have to have this property, 1, 2, 3, something like that. Okay? They have to follow these properties. Yeah, here it's hard to imagine. Yeah, but when we get there, here I'll give you some abstract idea here. Okay. Yeah. Later, I need to give you the details. What are those properties? What are those common properties? Okay. Yeah. All right. Yeah. Let me move to the next question. Number 9, is it possible that a computing problem with a larger size could be easier than this problem with smaller size? Yes. Yeah. Yeah. This question, if you're familiar with the notes, in the notes I explain, I use one example. Yeah. So if you still remember that, when I talk about prime factorization question, okay, when I talk about prime factorization question, remember when we derive the formula for the Horner's rule, we need to do factorization. Yeah, we need to do factorization. Yeah, But at that time, when we do factorization, I give you an example where n equals 1,000. 1,000. It's very easy to factorize number 1,000, right? Yeah. So 2 times 5, yeah. 2 to the third times, 5 to the third, okay? 2 cube times 5 cube. Factorization, so easy, okay? But if I give you a smaller number, 357, now it's much harder to do prime factorization, right? The number is smaller than 1,000, but it's harder to do factorization, okay? So we need to do a lot of calculation. Think about that, yeah? And here, this number and this number here, we treat as the problem size. Yeah, yeah, because this here, the problem size is different from what we used before. When we have an array, we use the number of elements in the array as the problem size. But here, there is only one number. So what's the problem size? It is the magnitude. Yeah. So there is another possibility, another case when we talk about problem size, we use magnitude. Yeah. Yeah. So it is a valid problem size. Yeah. Yeah. So I used this example before. Yeah. So if you still remember that, yeah. So you can choose the right answer. Yeah. All right. So our last question. Yeah. When we solve the element, yeah, all right, yeah, what's that? Element uniqueness problem. Yeah, there's another question. Check if you are familiar with the notes. Yeah, answer is yes, right? Yeah. So here in this quiz, because we have two methods. In the notes, method 1, method 2. Method 1, the brute force. Yeah, we work on it directly, the brute force. The growth function is n squared. Okay, yeah. Method 2, we sort the array first. Then we do adjacent comparison. Do comparison only on adjacent two elements. That one, the growth function is n log n. N log n. And we know n log n is better. Better. Better, yeah. Too slow. This whole quiz relatively hard. Yeah. So most of you didn't do well. Yeah. But you can still see a few questions. Very simple, like this one. Actually, this number 9, number 10, both based on notes material directly. Okay. Yeah. So number 9, number 10. If you are familiar with notes, you can get it easily. And there is another one I remember also based on notes. Yeah, look at number 5 based on notes, right? Number 6, apply the formula from the notes. Yeah, so we can also treat as relatively easy questions. Number 3, easy, right? Question types. Number 4, also not hard, yeah. So then, yeah, number 1, so probably, yeah, so you may know that, good. And yeah, number 2, yeah. So number 1, number 2, a little confusion for you. And the two other questions, probably you'll feel harder. Yeah, let me see. Yeah, not this one, yeah. So the number 8, yeah, number 8. So what I feel what I feel, number seven should not be that hard. The middle, in the middle level. Yeah. Number 8, yeah, we can treat as a hard one. Yeah. So 3 questions relatively hard. Number 1, number 2, number 8. Yeah. The other questions are actually not that hard. Yeah, not that hard. Yeah. But for those of you who did not do well, yeah, actually remember our rules. You can drop 2 lowest quiz scores. Yeah, lowest 2 quiz scores. To control the damage. Yeah, the damage should not be that big. Based on our rule. Yeah. But the most important thing, you need to understand, why you missed those questions. Yeah. Because in the midterm, all the questions, I will not give you brand new questions. The questions, basically, I do some modification on our 3 assignments. Quiz 1, quiz 2, and homework assignment number 1. Yeah. Okay. Yeah. So in that way, still not easy. Yeah. So even that, still not easy. Yeah. Yeah. So that means you need to, really do some hard work, do some, high quality study. Yeah. Then you can do well. Yeah. So we know this course is hard. Yeah. All right. Yeah. So I finished both quizzes. Now we have about 10 minutes left. Do you have any question to ask? Especially related to the homework assignment. Yeah. Number 25. Yes. All right. Let me look at number 25. Yeah. So here I have this. Yeah, the last question. The last question. Oh, this one. Yeah. All right. So this question actually, also number 14. Oh, all right. Number 25. Yeah. All right. Let me quickly finish number 25, then number 14. All right. Number 25, solve this array, but you already know x1 less than x2. Okay. This information can save you 1 comparison. Remember? Yeah, because after your first comparison, assume you do first comparison on x1, x2. Okay. Yeah. As a result, this is the result based on your first comparison. So the first comparison is saved. Okay. All right. Then try your best to the remaining work, although it may not be easy, but do you remember the lower bound formula before? Lower bound formula we just talked about, right? Then we just did it. Without first comparison, the minimum number of comparisons, right? Yeah. But after the first comparison, do you get it? Yeah. The remaining work, how many comparisons you need for the remaining work, right? Yeah. But here, remember, this is solution. I do not ask you for the answer. For the solution, you need to provide me the details. When you see solutions, not answers. Yeah. Our other questions, so here you can see, when I say solutions, you need to show me the detail. For answers, you do not need to show me the details, okay? Answers. But for answers, if you want to get partial credit, it's better to give me some critical steps or main formulas. Yeah. So for answer type, short answer type question, although it's not necessary to give me the details to get partial credit. You like to get partial credit, right? Credit. Okay. So you can do, even give me give me the main steps or main formulas. Okay, yeah, just you know, the most important information you feel related to this question. Okay, then so even your answer is not correct, so I can give you partial credit. Okay, yeah. All right, so yeah, log base 2 n factorial formula can be used to find the minimum, right? To find that minimum number comparison. That's correct. All right, but for the solution, that formula does not give you the detail, right? That formula for our question number 25. So in your mind, you know there is a correct answer. Okay, that's the goal. That's the target. That's the target, telling you, you know, that's the correct goal. Okay, but how to reach that goal? You need to do some work. Okay, you need to do some work. Yeah, so you need to do some comparisons. You use our, yeah, so here the type of work I expect you to do. Yeah, let me see. Let me bring up the yeah, the type of work I expect you to do. Question number 7. Do you remember how I did that comparisons to sort 3-element array? That kind of work. Okay, so your first comparison, your second comparison, your third comparison, you know, yeah, try to give me that kind of details. Okay, to earn full credit. All right, to earn full credit. Otherwise, just partial credit. Okay, yeah, otherwise just partial credit. Yeah, all right, yeah, so let me, yeah, 5 minutes left. Yeah, let me go to question number 14. Madison asked me, when it says x3 is in place, yeah, in place, does that mean it has no, all right, yeah, that's a question, or just that is the third element. Oh, yeah, let me clarify. Yeah, you ask a very important question. Yeah, let me clarify it. Okay, all right, number 14. No, yeah, here, right here. X3 is in place. That means, yeah, so first, this array not sorted. Yeah, this array not sorted. Okay, not in order. Okay, yeah, but when it is sorted, x3 is the middle one. Its position is in the middle. Okay, is the middle one. Okay, yeah, yeah, but in the original array, you know, in the, yeah, yeah, so original array, yeah, before it is sorted, you know, it is also in the middle, right? But after it is sorted, it is still in the middle. Okay, yeah, but nothing to do with no inversion or not. Okay, you still you could have inversion related to x3. For example, x1, x3, there could be an inversion between x1 and x3. Okay, and there could be an inversion between x3 and x5, something like that. Yeah, so there could be certain number of inversions with x3 involved. Okay, yeah, that means you should not eliminate x3 when you count the number of inversions. You should not do it in that way. If you do it in that way, you may miss a certain number of inversions. Yeah. All right. Yeah. Yeah. So when you do the counting, yeah. So here, my suggestion, when you do the counting, first, ignore this condition first, okay? Ignore this condition. First. Okay? That means forget about this X is in place. Yeah. Then you'll find the maximum number of inversions. Yeah. So you can get an answer without this condition. After you get the maximum answer, then you put this condition back and see how much change you need to do. Think about that. How much change you need to do before you remove this condition and after you add this condition back, and see what is the difference. Yeah. After you do things like that, you should get the answer. Okay? You should get the answer. Yeah. All right. Yeah. Other questions? Let me check. Yeah. All right. It looks like, oh, let me see. Yeah. All right. Okay. It looks like, yeah. So you pretty much get what you need. Yeah. So, all right. Just, try your best. Yeah. For those students who have already submitted, you can do resubmission, right? Yeah. Because you have 3 attempts to submit. I use your most recent submission for grading. When I do grading, I will use your most recent version. Okay? Yeah. So your most recent automatically overrides the previous version. Yeah. So if you feel after today's class, you feel you can improve your solution better, you can get a better grades, yeah, you can submit another version. Okay. Yeah. And remember, if you can submit it by midnight today, yeah, so before the deadline, yeah, you can earn 4 bonus points. All right, 4 bonus points. That's one question. Okay? One question is worth 4 points. Yeah. So that means you get 1 full question points for the bonus. Okay. Yeah. All right. So that's it. Yeah. So let's stop right here. Yeah.